Hello guys, today we start to study chapter 6, Electricity and Magnetism. This chapter contains 19 sections divided into 4 parts. We will learn about electric charge and interaction, electric current and Ohm's law, magnetic field and the magnetic force on current, and electromagnetic induction and a transformer. Electric charge, usually denoted by Q, is a fundamental property of some elementary particles. There are 2 types of electric charge: positive charge and negative charge. They can interact with each other. Like charges repel one another, unlike charges attract one another. A neutral object does not have a net electric charge because it contains equal amount of positive and negative charges. What is electric charges? To answer this question, let's look at atomic particles. Matter is composed of atoms. Atoms are composed of 3 types of particles: proton, a positively charged particle; neutron, an electrically neutral particle; and electron, a negatively charged particle. Therefore, a negatively charged object contains actual electrons, while a positively charged object contains actual protons. An atom consists of a nucleus that contains protons and neutrons and electrons that move around the nucleus. A different type of atom contains different number of atomic particles. We will learn more about atom and the nucleus in more details in chapters 8 and 9. The unit of electric charge is defined as Coulomb, shortened by C. The basic quantity of electric charge is experimentally determined as E equal to 1.6 times 10 to negative 19 Coulomb. Protons charge is E, positive E, while electrons charge is equal to negative E. Coulomb's law is a law telling us about the charge interaction. It says that the force between 2 electric charges is inversely proportional to the square of the distance between the 2 charges, and directly proportional to the product of magnitude of the 2 charges. The expression of this law is Fq equal to K times Q1 times Q2 divided by R squared. Here K is a constant, given by 9 times 10 to 9 Newton meter square per Coulomb square in the SI unit system. For example, find the electric force between 2 charges of 8 microcoulomb and 4 microcoulomb if the distance between them is 4 cm. For Coulomb's law, Fq equal to K Q1 Q2 divided by R squared. We substitute 9 times 10 to 9 into the constant K, 8 times 10 to negative 6 into the charge Q1, 4 times 10 to negative 6 into the charge Q2, and 4 times 10 to negative 2 into the distance R. Here we have changed microcoulomb to 10 to negative 6 coulomb and the centimeter to 10 to negative 2 meter. The result for the electric force is then obtained as 180 Newton. Another example is to find the electric force between proton and electron in a hydrogen atom. This is also the centripetal force for the electron orbiting around the nucleus. a single proton with a circular radius of 5.3 times 10 to negative 10 meter. Using Coulomb's law and substituting the constant k proton and electron charges and the distance of all radius into the expression, we can find the electric force to be negative 8.2 times 10 to negative 10 Newton. A charged object can also electrically attract an uncharged object through separating the negative and the positive charges in the uncharged object. You can try to do an experiment by using a ball pen after rub it with your nylon cloth to attract a small piece of paper. Previously learned gravity is a force between masses. It is always attractive and governed by Newton's gravitational law. Fg equals G m1 m2 divided by r squared. Gravitational force dominates on cosmic scale. The electric force that we learn from this chapter is a force between electric charges. It is repulsive for like charges and attractive for unlike charges, and governed by the Coulomb's law. Fq equals K Q1 Q2 divided by r squared. Electric force dominates on atomic scales. Electric charge can flow. Substance through which electric charge can flow readily is called conductor. Metals are usually conductors, such as copper, iron, etc. Inside a conductor, there are many free electrons as current carriers. Substance that strongly resists the flow of charge is called insulator, such as plastic, rubber, glass, wood, etc. Inside an insulator, electrons are tightly bounded by the atoms and hence cannot flow. Substance whose electric conductivity is between conductor and insulator is called semiconductor, such as silicon, diamond, and so on. Semiconductors are used to make transistors, whose conductivity can be changed at will. Substance through which electric charges can flow freely without losing energy is called superconductor. Superconductivity is a phenomenon of low temperature. Some materials, when they are cooled to a critical temperature or below, become superconductor. For example, aluminum becomes a superconductor when it is cooled to 1.2 Kelvin, below zero Celsius, below zero by 272 degrees in Celsius. To quantitatively describe the charge flow, we define electric current as the rate of charge flow. Charge flow per unit time. That means for charge Q to flow through a cross-section by time t, we have the current equal to Q divided by T. From the current formula, we can see that the unit of electric current is simply derived as the coulomb per second, renamed as ampere, shortened by A. Therefore, 1A equals 1 coulomb per second. A circuit is a closed path that conducts electric current. A battery can do work to move charges and thus drive a current through a circuit. The work done by moving a unit charge from one point to another point is defined as the electric potential difference between the 2 points, denoted by V, with another name as voltage. Therefore, the electric potential difference V equals the work done W divided by charge Q. V equals W over Q. The unit of the electric potential difference is therefore joule per coulomb, named as volt, shortened by V. For instance, the voltage of a car battery is 12 volt. Ohm's law governs the electric current through a wire when the electric potential difference is applied. This law tells us the current is proportional to the electric potential difference applied to the ends of the wire, but inversely proportional to the resistance of the wire R. The resistance R is a measure of opposition to the flow of charge. The resistance of a metal wire depends on wire composition, length, cross-section area, and temperature. The unit of resistance is ohm, defined from volt per ampere. 1 ohm, the capital omega, equal 1 volt per ampere. Electric power is a quantity defined as the rate at which a current is doing work. Dividing the current work done, Q times V, by time t, replacing the ratio of Q and T as current I, we have the electric power is given by the product of current I and the voltage V. So P equal IV. The unit of electric power should be the same as the mechanical power, and thus is a volt, shortened by W, defined from joule per second. So 1 W equal 1 joule per second, same as the mechanical work we learned before. For example, find the electric current and power when a 20 ohms resistance is applied with a 12 volt potential difference. From Ohm's law, we have the current I equal to voltage over resistance R. Substituting 12 volt into the voltage V and 20 ohms into the resistance R, we have the electric current equal to 12 divided by 20 equal to 0.6 ampere. Then multiplying the current 0.6 ampere to the voltage 12 volt, we have the electric power to be equal to I times V equal to 0.6 times 12 equal to 7.2 volt. This is the part of electricity of this chapter. Thank you. We will continue next time the second part about the magnetism. Bye.